Well, thank you very much. In fact, we're just now getting reopened after the pandemic. We closed down in March 2020, and the public outreach program here is only just now restarting. It's been a long haul, and forgive me if I'm a little rusty. Haven't done an awful lot of presentations lately. So with that, let me share my screen and we'll get started. Okay. Whoops, can everybody see the dome? And
we're good here, Steve.
Yeah,
okay.
we can see it.
Good. Okay. Well, yeah, I'm Steve Flanders. I work for Caltech, and I run the public outreach program at Palomar Observatory. Thank you for asking me to speak with you this evening. In his announcement, Jerry suggested that he thought I must have one of the best jobs ever. Well, in that, Jerry was right. It's been absolutely a hoot to be working at the observatory and to be close to what's going on and all of its history. I've been doing this for 13 years. 10 of those as a Caltech employee. I love telling the story, and now I'd like to spend some time talking with you about the science and engineering of Palomar Observatory. In the 1950s, this was a very important and famous place. There we go. While it is now no longer so famous, after 87 years of science operations, Palomar Observatory remains an important and productive contributor to the global scientific enterprise. I'd like to organize this presentation around 3 topics. First, our mission. Second, an overview of the facilities that support our science operations, that is, the telescopes and the instruments. And third, a summary of what we have contributed to science over these 87 years. Palomar Observatory is owned and operated by the California Institute of Technology. It was built with private funds, and now its operating budget comes entirely from private sources. There are 4 points for our mission statement. You see here, we support the work of professional astronomers. We train graduate students in methods of research. We engineer new science instruments, and we share our results with the public. In reading this list, please understand that this mission statement is aspirational in nature and does not necessarily describe what we actually do. And what we actually do can be described very simply. We convert starlight into data. We do it very efficiently and very reliably. On the Hale telescope, we maintain a suite of scientific instruments, imagers, spectrographs, photometers, and others for the use of the astronomers. During an observing run, they may use one or more of the science instruments to collect the data they need for their research. The data produced by the science instruments is our product, and the astronomers are our customers. Their home institutions pay a fee for each night of observing. Section 2, world-class science is being done at Palomar Observatory, and a certain infrastructure is needed to support that science program. In this section, we'll look at the property, the telescopes, and the current inventory of science instruments, that is, our tools of science. Palomar's science enterprise started in 1936 when an 18-inch Schmidt wide-field telescope went into service on the mountain. The dome that housed this telescope stands a quarter-mile east of the dome of the Hale telescope. Here's an overview of the observatory's property on Palomar Mountain in northern San Diego County. We are looking to the southeast across a plateau that lies at an elevation of 5,600 feet and encompasses the 2,200 acres that Caltech owns. San Diego is almost directly behind the position of the camera and 50 miles away. Los Angeles is also behind the camera, but more to the left of the frame. LA is about 90 miles away. Let me label and describe each of the domes that you see in this picture. Here we see the location of the dome from the previous slide. It once housed the 18-inch telescope Fritz Zwicky used in the 1930s to search for supernovae. The instrument was decommissioned in 1999 and is now on display in the observatory's museum. The dome now houses weather instruments. The designation P18 represents the shorthand we use when referring to the domes and the telescopes. Palomar Gattini IR is a near-infrared survey telescope that is housed in a small structure located behind P18. In this view, the building is obscured by trees. Although Gattini IR uses a 30-centimeter refracting telescope, the building in which it is mounted once housed a 20-inch telescope. So, since we have long memories up here, the building and the telescope retain the label P200. On the left is the dome of the 48-inch Samuel Oschin wide-field Schmidt telescope. Brought into service in 1948, this telescope was used to conduct the two Palomar sky surveys, the first in the 1950s, second in the 1980s. It now supports an optical all-sky transient survey named the Zwicky Transient Facility, or ZTF. This is the observatory's Discovery Telescope, and in the last section of this presentation, we'll talk a bit about its role in ZTF. To the far right is the Palomar 60-inch telescope. It was built to take some of the observing load off of the Hale telescope and was commissioned in 1970. P60, as it is known, now operates robotically as part of the ZTF system, where it uses a low-resolution spectrograph to automatically categorize discoveries made by the 48-inch telescope. It has a Ritchie-Chrétien optical configuration. The 200-inch Hale telescope began science operations in 1949. It remained the largest effective telescope in the world until the first of the 10-meter Keck telescopes went into service in 1993. The 1-meter Winter telescope is located several hundred yards west of P200, a recent addition. Its dome was not in place when this photograph was taken. Winter is a robotic near-infrared synoptic survey telescope. Winter and Palomar Gattini IR have complementary but slightly different objectives that we'll talk about toward the end of this presentation. To summarize, there are 5 active telescopes on the mountain: 2 optical survey telescopes, 2 near-infrared survey telescopes, and 1 general-purpose research telescope. The 4 survey telescopes operate robotically and are Q-scheduled. The 48-inch Samuel Ocean telescope is seen in the top row at the left, with the 60-inch telescope to its right. Both are now dedicated entirely to ZTF. On the second row, we see the 30-centimeter Gattini IR telescope, and to its left, the 1-meter Winter telescope. Both observe at near-infrared wavelengths. We refer to these 4 instruments as our discovery telescopes because their function is to repeatedly image the sky and find things that either have changed or have perhaps never been seen before. The 200-inch Hale telescope is used for spectroscopy, photometry, and imaging, at visible and near-infrared wavelengths. The instruments used for imaging and photometry are mounted at prime focus at the top of the tube. Prime focus is an f3.3 modified Newtonian optical system. Spectroscopy is done at Cassegrain focus, an f16 system at the bottom of the tube. Our adaptive optics system is installed at Cassegrain focus. Observing nights are assigned to astronomers by a time allocation committee. Time on the telescope is granted to professional astronomers and graduate students who are conducting original research projects. In service for 73 years, this is the last major astronomical telescope to use a thick single-piece mirror cast from 14.5 tons of borosilicate glass, or Pyrex as they used to call it. The mirror is not rigid. Instead, its shape is maintained by 36 mechanical levers that support the mirror from behind. It is also the largest telescope ever built on an equatorial mounting. No larger equatorially mounted telescope was ever constructed due to weight limitations. In fact, the moving parts of the telescope seen here weigh 530 tons. The telescope turns in right ascension on high-pressure oil bearings. The oil system was a major innovation in the 1930s, and still today, it allows the telescope to turn with so little friction that for its first 70 years, the telescope's tracking in right ascension was driven by a 1/12 horsepower motor. What follows then is a list of the 9 science instruments astronomers may use when observing on the Hale telescope. These 9 instruments are grouped into 3 categories of 3 instruments each. First, 3 seeing limited instruments installed at prime focus. Second, 3 seeing limited instruments installed at Cassegrain focus. And third, 3 diffraction limited instruments installed at Cassegrain focus. The 3 seeing limited instruments used at prime focus are the wafer scale imaging for prime, or WASP, a visible light imager, the wide field infrared camera polarimeter, or work-POL, a near infrared spectropolarimeter, and Chimera, a high-speed imager photometer. The three seeing limited instruments at Cassegrain focus are, first, the Cosmic Web Imager, a multi-wavelength integral field imaging spectrograph that was developed at Palomar as a prototype for a similar instrument now in service on the 10-meter Keck telescopes at Keck Observatory. Second, the double spectrograph, our most frequently used instrument, is a single object visible light spectrograph that has been on the telescope for more than 3 decades. Third, the triple spectrograph, which operates at near infrared wavelengths, used for single object spectroscopy, and happens to be, it's becoming progressively more important instrument as our skies deteriorate due to light pollution, the light pollution that is growing all around us. And the third category, 3 diffraction limited instruments at Cassegrain focus are, first, the Palomar High Angular Resolution Observer, FARO, a near infrared imaging spectrometer. And second, the Palomar Radial Velocity Instrument, PARVI, is a high resolution infrared spectrograph and coronagraph used for precision radial velocity studies. Both of these 2 instruments require support of PALM 3000, our adaptive optics system, a system that takes the twinkle out of starlight. Under favorable conditions, PALM 3000 allows FARO and PARVI to operate at nearly the Hale telescope's theoretical diffraction limit of 0.0565 seconds of arc at 1140 nanometers wavelength. That's a bit of a, well, that's a bit of a go. Anyway, science and engineering, section 3. Well, these telescopes and these instruments are the tools that make it possible for us to do world-class science. With that in mind, let me draw up an account of our contributions, as we see it, to the practice of engineering, to the science of astronomy over the last 9 decades. I'll summarize this broad topic under 6 general headings. These are the 6 areas of scientific research and engineering practice, which over the years, Palomar astronomers have been most concerned with. These are also the areas that continue to dominate our work. I'd like to touch upon each of these subjects, but first, well, I need to point out perhaps an obvious limitation. In these things, more actors are involved and more subtleties arise than can be addressed in a short discussion like this. The goal of this presentation is to describe the roles that Palomar astronomers have played in the most important advances in astrophysics of the last 9 decades. To do this, many details must be omitted, and the work of many contributors must go unmentioned. This is especially true of the much abbreviated discussion of the work of Edwin Hubble that follows. I'll begin with the historical context. Many of Palomar Observatory's early science programs were continuations of work initially undertaken at Mount Wilson Observatory, home of the 100-inch Hooker telescope, the world's largest from 1917 to 1949. One of the most important of Palomar's early science program, early science programs built upon two immensely significant discoveries Edwin Hubble made at Mount Wilson in the 1920s. First, that the universe contains not one, but many millions or billions of galaxies. And second, that with just a few exceptions, every galaxy we see is moving away from us at a rate proportional to its distance. Hubble's discovery of the expansion of the universe set off a race to determine the rate at which the universe is expanding. For many reasons, Hubble was never able to arrive at a generally accepted value for what we now refer to as the Hubble constant. His estimates predicated a young and small universe that contradicted theories in other fields. At one point, for example, he postulated a universe that was younger than the things it contains. His difficulties were, to a large extent, related to limitations in the design and construction of the 100-inch telescope. And the Hale telescope was built in large part to overcome those limitations. So, with the start of science operations in November 1949, the problem of determining the rate of cosmic expansion passed to Palomar Observatory and the Hale telescope. Observing at Mount Wilson and later at Palomar, Walter Baade took up this problem. He found two distinct populations of variable stars in the Andromeda galaxy, M31. From this discovery in 1953, he produced a revised estimate of the expansion rate that doubled our understanding of the size of the universe. But even so, contradictions in the data remained, and investigations by others continued. Finally, in the late 1950s, observing on the Hale telescope, Caltech astronomer Alan Sandage made his own calculation of the expansion rate and published a value for the Hubble constant of 75 kilometers per second per megaparsec. His estimate is consistent with recent values obtained by the Hubble Space Telescope and other ground-based instruments, which is to say, to a close approximation, at Palomar Observatory, we correctly determined the age and size of the universe. This is often cited as our most significant contribution to the science of astronomy. And we probably are all familiar much of this, but let me ask, why is this number so important? Well, to put it simply, the expansion rate is important because everything we know about the universe beyond our own galaxy depends upon knowing speed and distance. The adoption of a generally accepted value for the Hubble constant made it possible to use redshift as an indicator of absolute distance and of chronological age. As this diagram may suggest, the Hubble constant underlies and enables many subsequent discoveries. To illustrate that relationship, let me cite an example from Palomar's science programs, in which later discovery was dependent upon Sandage's findings. Well, among the many extraordinary discoveries in the distant universe facilitated by the Hale telescope, one of the most important was the identification of the radio loud source 3C273 by Martin Schmidt, Alan Sandage, and collaborators in 1963. Schmidt knew this object lay at a great distance because he could see that the lines in its spectrum were strongly redshifted. In fact, using the value Sandage had obtained for the Hubble constant, Schmidt calculated that 3C273 was 2.5 billion light years away, at the time, one of the most distant objects ever seen. But this distance meant that its intrinsic luminosity must be hundreds of times that of the Milky Way. No physical process known at the time could account for such a vast production of energy. In this instance, an accurate value for the Hubble constant was of critical importance for two contrasting reasons. First, Schmidt's discovery was entirely dependent upon the value for the Hubble constant that Sandage had derived. Had he used Edwin Hubble's earlier estimate, for example, Schmidt would certainly have looked at 3C273 spectrum and concluded that the object was relatively close to Earth. As such, its luminosity could have been accounted for by known physical processes. Well, but only in the much larger and much older universe modeled by Sandage did the extraordinary character of 3C273 become strikingly apparent. This example shows why Sandage's publication of what I'll call a correct value for the Hubble constant was of such great importance to the advance of cosmology and science in general. But if Schmidt's discovery was dependent upon Sandage's earlier work, then it is also true that many later discoveries were dependent upon what Schmidt had done. Specifically, Schmidt's discovery raised important new questions that sent astronomers around the world hurrying to find the source of 3C273's power. Eventually, they realized that this and other similar objects lay at the centers of galaxies. Soon, this research led to black holes and to the idea that the enormous energy output of these galaxies was generated by the accretion of gas and dust around black holes at their centers. We now know that supermassive black holes reside in the nuclei of virtually every large galaxy, an idea recently confirmed in images taken by the Event Horizon Telescope. All of which is to say that at Palomar Observatory, we opened the door to investigations of the high energy universe. We count this as our second major contribution to science. And in both these discoveries, spectroscopy was the essential tool that enabled the work of Sandage, Schmidt, and many others. In fact, the analysis of the spectra of astronomical objects is the most powerful tool we have for understanding the physical processes at work throughout the universe. Spectroscopy is indispensable to the science of astrophysics. And once it was established that the universe had a beginning, spectroscopy was used to determine its chemical composition and, at Palomar, to demonstrate that this composition had evolved and grown more complex over time. Caltech astronomer Jesse Greenstein, it seemed obvious that the universe had become, chemically more complex. Ideas about the Big Bang gave him reason to believe that the universe had started out with a very simple set of elements. From this premise, he could prove that sometime between its simple beginnings and the present day, a great elaboration had taken place in the chemical complexity of the universe. Working on the Hale telescope, he constructed his proof by analyzing the spectra of hundreds of stars near us in the Milky Way. The result was a catalog that enumerated and measured the chemical abundances of our galaxy and, by extension, of our universe. His work quickly led to a scientific collaboration with nuclear physicist Willie Fowler. And it was Fowler, together with Fred Hoyle and Margaret and Jeffrey Burbidge, who solved the puzzle of how stars synthesize heavy elements from lighter ones in nuclear reactions in their cores. In 1983, Fowler received the Nobel Prize in Physics for his theory of nucleosynthesis. At Palomar, we consider our participation in the development of the theory of nucleosynthesis as being our third major scientific contribution. And the Palomar Observatory continues to play a role in the exploration of the chemistry of the universe. Caltech's LIGO observatories have recently observed gravitational waves produced by neutron star mergers. The 18-inch Samuel Oschin telescope has helped locate the glows produced by these events, what we now call kilonovae. And spectrographs on the Hale telescope have helped analyze the content of these objects. This work has closed a gap in the theory of nucleosynthesis. Indeed, the theory put forward by Fowler and the others could not account for the creation of the heaviest elements. They knew that the heaviest elements must originate not in the cores of dying stars, but in unknown processes capable of generating much, much greater energies. Such processes were discussed by the theorists, but Fowler knew that none of their theories were supported by observational evidence. Well, however, we now have that evidence. Spectrographic analysis of recent kilonovae confirms that gold, platinum, and other heavy elements are synthesized in the merger of neutron stars. This new knowledge was enabled by advances in technology coming from Caltech and other institutions. Well, speaking of technology, Caltech really likes technology, and Palomar Observatory's services continue to be in demand, in part because Caltech is committed to the design and engineering of the world's most advanced science instruments. Often, the development and prototyping of new devices is done on the Hale telescope. As a result, Palomar astronomers always have access to the latest technology. A tradition of innovation and technical excellence runs through Palomar's history. In the 1930s, for example, Caltech developed a vacuum deposition process that puts a thin coating of aluminum on a glass surface. You see here the mirror of the 200-inch telescope. This process replaced silvering for astronomical mirrors. Technological innovation, yes, well, we have made a great many technical innovations. The first electronic detector for astronomy, a pulse counting photometer, was installed on the 200-inch telescope in the 1950s. Computers for telescope control and data acquisition were introduced in the 1970s. Photomultiplier tubes were used until, toward the end of that decade, Jim Gunn and James Westphal developed the first digital camera for astronomy using 4 800 by 800 CCD chips. Four-shooter, as it was known, was able to reach magnitude 24 in 60 seconds on the Hale telescope. By contrast, the ZTF camera seen here reaches 20.5 magnitude in 30 seconds. Now, in the Smithsonian Institution, four-shooter was built as a prototype for the Hubble Space Telescope's wide-field planetary camera. Palomar Observatory has also been at the forefront. The development of adaptive optics, Palm 3000, our adaptive optics system, has a wavefront sensor that detects errors in the light path caused by motions in the Earth's atmosphere and by defects in the optics. Operating in real time, the system calculates the precise inverse waveform and passes this information to 3,380 actuators on the back of a deformable mirror that move up to 1/2 wavelength of sodium light 2,000 times a second. Our first adaptive optics device was commissioned on the Hale telescope in December 1919. In fact, using the adaptive optic systems that have been developed on the Hale telescope, we are able to image exoplanets directly. Excuse me. By attaching an imaging spectrograph and a coronagraph to Palm 3000, and by taking a sequence of images at increasing wavelengths, we can image an exoplanet and know what it, or at least its atmosphere, is made of. I think it's a neat trick for an old telescope like this. And I should point out that the people who built the telescope in the 1930s firmly believed that we would never be able to see planets orbiting other stars. We are doing it with the telescope that they built. The adaptive optics is one tool among many that astronomers bring to their study of exoplanets and brown dwarfs. The goal is to detect, image, and characterize objects that are too faint, too far away, and too close to their host stars to be observable by conventional means. Because direct imaging is rarely achievable, most of the tools and methods of exoplanet research that you see here use indirect and inferential measures. But our adaptive optics system has also been useful for work involving objects much closer to home. That is to say, objects in our own solar system. Palomar Observatory has a tradition of discovering and studying the small objects of our solar system. These studies have resulted in a richer understanding of our solar system's architecture. A moment ago, we saw a view of Neptune taken with the adaptive optics system. Here, this system is used to observe Saturn's moon Titan as it occults a double star on December 20th, 2001. It's a remarkable bit of footage. Watch as the light from the stars is refracted around Titan's limb. And this one is going to pass, and you'll see the refraction go around the south side of the moon. These refractions provided astronomers with information about the depth and density of Titan's atmosphere. Starting in 2001, Caltech astronomer Mike Brown and his collaborators began discovering many small objects orbiting the sun beyond Neptune, what we now call the Kuiper Belt. His discovery of Eris prompted the International Astronomical Union to alter the meaning of the term planet in a way that removed Pluto from the roster of planets. Yes, we helped kill Pluto. The change in name necessitated the creation of a new designation, dwarf planet, as Pluto, Eris, and others are now classified. Astronomers at Palomar have observed our solar system as it changes and evolves. On March 24th, 1993, Carolyn Shoemaker discovered a comet, later named Comet Shoemaker-Levy 9, on photographic plates taken with the 18-inch telescope. Calculating its previous motion, she realized that the object had recently passed close to Jupiter, and it soon became apparent that, during the encounter, the comet had broken into a chain of fragments. Well, then calculating its orbit forward in time, she also realized that the comet would crash into Jupiter's atmosphere in July 1994. Colliding with the planet's southern hemisphere on July 16th, 1994, the chain of fragments continued to fall into the cloud tops for 7 days. The event was viewed by professional and amateur astronomers around the world. The impact scars persisted for many months. Note that this event came to our attention because Carolyn Shoemaker was using the telescope to photograph the sky, to map its contents, and to look for transient objects. In effect, she was doing a survey. And in our last section, our sky survey programs have been and continued to be the most broadly impactful scientific contributions made by Palomar Observatory. The two wide-field Schmidt telescopes, the 48-inch Samuel Ocean telescope, and until 1999, the 18-inch Schmidt telescope, have been the observatory's engines of discovery. These telescopes have served this role because they have usable fields of view several hundred times that of the Hale telescope. As seen in an earlier slide, the ZTF survey camera on the Samuel Ocean telescope records 47 degrees of sky on each exposure and is able to record the entire visible sky once every 2 nights. And in fact, while also imaging the band of the Milky Way twice a night. This old 48-inch telescope is an ideal instrument for repeatedly imaging and mapping the sky. Well, got to go back. Hang on. There we go. For years, we found comets and other transient objects by conducting photographic surveys. For almost 60 years, the 18-inch Schmidt telescope was used for supernovae searches and for mapping galaxy clusters, as well as for minor body detection. 6 major surveys were completed with this telescope before it was decommissioned in 1999. Of the 6, the Palomar planet-crossing asteroid survey, which ran from 1973 to 1995, was probably the most influential and the most effective at raising awareness of the potential for asteroid collisions. During this period, Eleanor Helene and Jean and Carolyn Shoemaker discovered more than 100 near-Earth objects. In 1948, the 48-inch Samuel Ocean telescope began producing a series of astronomical surveys that remain scientifically relevant. Its first 5 decades of operation were dedicated to photographing and cataloging Palomar's visible sky, as well as to conducting supernovae searches and making stellar proper motion measurements. Currently, this telescope is dedicated to ZTF's program of repetitive imaging. By comparing recent images to older images, the system has detected thousands of transient objects, variable and pulsating stars, flares, novae and supernovae of all types, remnants of gamma ray bursts, AGN eruptions, and a variety of other phenomena. Operating robotically, the 48-inch telescope is the Discovery Telescope for the Zwicky Transient Facility and for the observatory. And finally, Palomar Gattini IR has been in operation for several years. Its job is to take wide field images that are used to create a catalog of objects in the near infrared sky. No such inventory has ever existed before. And now this telescope is finding nebulae and other objects that have never been seen at visible wavelengths. Commissioning of the Winter Telescope is almost complete, and soon it will begin a synoptic survey of near-infrared transients using technologies similar to those used with the Samuel Ocean Telescope from ZTF. With that, so we've looked at the telescopes. We've described their individual roles and listed the Hale telescope's specialized science instruments. Then we divided the science of Palomar Observatory into 6 subject areas and discussed at least some of the contributions and advances that the system's made. I'll ask you to consider one key takeaway. Please notice the interconnectedness and codependencies that link together our many disparate areas of research. In the long run, studies in one area tend to inform other studies, many other studies. And well, that's how we get science done at Palomar Observatory. George Ellery Hale founded this observatory, and he had a motto: make no small plans, dream no small dreams. With that, thank you again for giving me this opportunity to speak with you. And at this point, I'd love to do questions. I'd just love to talk about it. So thank you.
That was so great. Thank you.
Again, if anybody in the room here has questions, just come up to the microphone. Excellent presentation, Steve. I think we really enjoyed that. Laura, go ahead and kick us off. I know you've got a ton of questions for him.
I do. Why don't we wait till anybody who is there physically to ask questions, and then I've got a couple, 3, maybe?
Maybe, of course.
Okay.
Hey, I am Jerry. I'm the one that thinks you have that fantastic job. Great presentation. I had a question about the focus points. There's a primary focus point and a Cassegrain focus point. where different instruments are placed. Do you have a diagram or a photo that would show some of the instruments at those points?
Show the instruments or show the light path?
Or even just show where those focus points are on the telescope?
Simple answer is yes. Complex answer is I don't quite know how to get to it. There is a diagram by Russell Porter, famous cutaway diagram of the telescope, and you can find it on Palomar's website. And
Okay.
that may be the easiest way to get at it. Because, well, as I say, I just got a new computer and all of my files right now are not real well organized for finding things like that. But the diagram shows the prime focus at the top of the telescope. Prime focus looks directly at the mirror. There's no secondary mirror in the way as in conventional Newtonian telescopes. For Cassegrain focus, there are a series of convex mirrors that are held the bottom of the prime focus cage and can be moved into the light path to send light down to the instruments at Cassegrain focus. We can move from Newtonian focus to Cassegrain focus in about 20 minutes, and occasionally they do it during an observing run. To make things a little more complex, there is another focal point. Doesn't get used much anymore, but it's called Coudet focus. And here we use a series of mirrors to send the light down through the south axis to a room at the end of the telescope. It's an F30 optical system. It was built for the spectroscopists who wanted large star images. They got them. As I say, it isn't much used anymore because now we do the spectroscopy at Cassegrain focus. But yeah, I can't immediately find that diagram. I'm sorry. Forgive me.
No, I will look that up. Thank you.
Other things, questions, discussion. Coca-Cola.
Hi, I do have one question, a couple questions for you, Steve. I'm just curious how bad the light pollution and actually the particulate pollution has gotten up at Palomar over the years. I mean, on an average night, can you see 6 magnitude? Can you see 7? Or are we down to 4?
Well, let me put it this way. Caltech bought this property in 1934. One of the reasons for locating the telescope here was that at Mount Wilson, which sits right above Los Angeles, familiar with it, the performance of the 100-inch telescope was being degraded by light pollution.
Right.
And well, Mount Wilson has better seeing than we have here for the most part. But at the time, this, hard to believe, this was one of the darkest spots in the country. George Ellery Hale said, oh, they'll never have a problem here. Well, famous last
Right.
The horizons are getting brighter and brighter every month. There's development all around us. Fortunately, the sky within 45 degrees of the zenith is still in reasonably good shape.
Okay,
And yes, in that region, well, my eyes can't really do it anymore, but I have been told that 6th magnitude and beyond is easy to reach for for younger people.
okay.
You know,
And the regular smog drifting over from San Diego has not been too bad?
well, by and large, San Diego doesn't generate a lot of smog. LA is the real
Right.
problem in that area. And at 5,600 feet, generally we are above it. The layer stays low. We can see clouds of this stuff moving along to the north past the San Bernardino Mountains. It doesn't tend to get up this high. So,
All right.
yeah,
I was just wondering, thanks.
thank you. Other things, anybody, please.
Hey, Steve, it's Eric.
Hey, Eric.
I'm the one,
Hi,
I'm
Eric.
the one that we've been responding with over the email.
Yep.
I have a question on the original sky survey. Do you know what has happened to the original glass plates, where they're located, or after they've been digitized? Are they still
question.
around?
Oh, absolutely. And they're still considered important, contain important scientific data. They're still consulted occasionally, even though we have digital copies now. And the plates are all in very secure, very rigid boxes, specially built to hold them. And the boxes are located in the basement of the 60-inch telescope. And
Very good, thank you.
yeah, I mean, if you know the right people, you can go in and take a look at them. Other things.
Well, if nobody else who's physically there has a question, I've got a couple for you, Stephen.
Sure,
And
please.
I've been trying to take a few notes, but I missed something. When you apply the adaptive optics, what kind of resolution did you say that you can achieve?
Well, you've got to have fairly good seeing conditions to begin with.
Uh-huh.
If the seeing conditions are really not very good, the whole system gets overwhelmed. But the theoretical diffraction limit of the 200-inch telescope is 0.0565 seconds of arc at 1140 nanometers wavelength. And we can come close to achieving that resolution.
Okay, so you do get close to that because, all right, that's really interesting. Okay, I'll do some work on that, on the math. And the second question that actually came up when we did a pre-presentation Zoom session on Tuesday about the Palomar Observatory. And a question rose up there that I couldn't answer, and I'm hoping you can, dealing with, again, how the adaptive optics works. We know we got these tons and tons of glass at the primary.
Yep.
And yet we got actuators, because this is not a segmented mirror. We've got actuators that move things. So where does that actually happen? Are actually mirror segments being manipulated, or is it done some other way?
It's done some other way. I believe it's true that in all cases, I don't think there's an observatory or a telescope anywhere where the adaptive optic system is actually implemented on the primary mirror. It's always done somewhere else. In this case, the deformable mirror, it's about 4 or 5 inches round and is located at the Cassia Green focus cage just above the focal point.
Okay.
Okay. The Gemini telescopes have built their deformable mirror into the secondary, which I thought was kind of a neat way to do it.
Yeah, right.
But we have it as part of the adaptive optic system at CAST Focus. And can I point out one of the things I found really fascinating about it is we always tell people that the adaptive optic system corrects for errors in the light path caused by motions in the Earth's atmosphere. And that's what it's supposed to do. But it's also true that it corrects for errors in the light path caused by errors in the optical system. Which is actually kind of neat. You don't have to have a perfect mirror.
Yeah. Well, that's what we saw with Hubble, right? They corrected it because of the problems with that. My question, maybe my third question is, you said that the adaptive optics can manipulate it at two thousandths of a second.
Yes.
Well, light still travels about what? About 800 miles in that time. 186 divided by 2, more than 800 miles. How does that work? If we got 2,000ths of a second and light can travel hundreds of miles in that thousandth of a second, how does that work?
Well, because once the corrections are made, or as the corrections are being made, it's only got like 4 or 5 feet that it's got to travel till it gets to the detector. And, and I guess part of the answer, I've never run into this question before. Part of the answer is that it's a backward looping system.
Okay.
In other words, the light comes in, looks at the wavefront, and then sends a correction to the mirror that is kind of behind it. It doesn't update on the next passage, the next 2,000ths of a second of the light, rather than on the light it's actually receiving.
Oh, okay.
Okay.
That's okay, great.
And I think on the Palomar website, I think there's a diagram showing how this works. It's really quite a neat system. It was originally a military application, and in the late 70s, the military started letting out some information about it, and it was quickly gathered, quickly scoffed up by the astronomers who have made extensive use of it. It's a neat system. And can I point out, you have a guide star. You have to have a guide star.
Yeah, of course.
because you got to have something to look at the incoming light path and to do the measurements. Well, we had a bright laser guide star on the telescope for a long time, but we are very close. We are way too near a whole lot of airports. And a lot of problem with that. So finally, we had to take down the guide star, which hasn't been a problem because virtually all of our usages of the adaptive optics system has had to do with exoplanets. And when you're looking for an exoplanet, by definition, you have a guide star in the field, the host star for the planet.
Block it out.
And now we are developing an ultraviolet guide star that hopefully will not have a problem with airplanes and things like that.
Great, thank you.
Well,
Thank you.
you. Any other things?
Thank you, Steve. I just had a question. I was curious, the astronomers and the scientists that are using the telescope, are they all Caltech scientists, or are other scientists and astronomers allowed to get time on the
They-
telescope?
They bid.
Well, this is privately owned, privately managed. Caltech has reserved for itself and its astronomers about half the observing time on the telescope. The other half we sell to partner institutions. The Jet Propulsion Laboratory has a 1/4 share of the time. Yale University has an 1/8 share of the time. And the National Astronomical Observatories of China have the other 1/8. And people from those institutions are the ones who can request time on the telescope. As I understand it, we charge something like $13,000 a night for observing on the telescope. A lot of money, but it's pretty cheap by comparison. The Keck telescopes cost something over $100,000 a night. We're cheap because this place is paid for. It was paid for with a $6 million grant from the Rockefeller Foundation in 1928. So one of the reasons we're still in business is that you can do a lot with this telescope. It ain't the biggest, but it also helps conserve your grant money. to put it in stark terms. That's one of the reasons they do it.
Stephen, I just have to comment. I'm wearing, you can't see it, but I'm wearing my JPL t-shirt tonight in honor of this presentation. But I almost wore my other shirt that I have from Caltech, and it says MIT across the front. And you go to the back and it says, because not everybody can go to Caltech.
Yeah, there's a lot of electricity between the two. George Ellery Hale was an MIT graduate.
Right, he was.
He helped found the institution. It's an interesting relationship all the way around.
Thank you, Stephen. This was really fun.
I love telling the story. It's been great fun
Thank
talking
you,
to
Steve.
everybody. Yeah,
Excellent presentation. Thank you.
thank you very much. With that, I'll say goodnight because I got to be here at 7.
Thank you very much.
Thank you very much. Bye-bye.
That was great.
Okay, great presentation. Eric, thanks for arranging him and great job. I think we all really enjoyed that.
Yeah.
Yeah, just
Yeah,
a few
definitely.
announcements there. Everybody have it on your calendar for Saturday, April 29th for the
Oh, yeah.
SAS potluck out at Oak Grove
Yeah.
Park.
Yeah.
give me life.
What is it, sir?
SAS. Yeah.
Oh.
4 p.m.
Are you guys seeing the share screen?
Yeah, 4
Yeah.
p.m. 4
Are you guys
p.m.
seeing the shared screen on Zoom?
Yeah.
Yes.
Okay.
Yeah, let me move this out of the way.
Ooh.
So while Eric's doing that, I'm going to pass the hat and we're all going to chip in. We're going to get a night or two of time on the Palomar telescope. Okay. $13,000 a night. It's affordable, right?
Oh,
Pretty much.
wow.
I know, Mike, you got more than that invested in your dumpy little telescope. A big sale. Okay. Okay, are you all on Zoom seeing our shared screen, the potluck announcement? Okay, very
Yeah.
good.
Yeah.
So we kick off the day at 4 o'clock. If you so choose to come out to the Nature Center, Doug is giving a presentation to anybody that's in attendance. He's got a Girl Scout troop coming out for that. He's put together kind of a cool presentation, the Artemis mission.
Alright.
Got one right now.
Oh, will you change topics or?
No. I've been doing on that evening, so I'm gonna hold off on that.
Gotcha, okay.
So you come out, if you guys are, anyone out there interested in helping out, Sandy and a bunch of Girl Scouts are gonna open up the Nature Center. They're gonna set up tables with all kinds of activities and so forth. So you can participate in that or help out there if you'd like. And then they're gonna wrap that up about 6:30, and then we will be over to potluck.
Okay,
And we'll be there for that.
arrive at 5 o'clock, between 5 and 5:30 for the potluck, because at 5:30 we eat. And you know, we're not gonna wait for you. Okay, right? So bring whatever you want. It's a potluck. It's total random and chaos. We'll see what happens, right?
Okay.
Okay, look forward to seeing you. And then that evening is astronomy in the park, our normal public outreach. So the weather should be nice and warm by then, and
Yeah.
we'll enjoy ourselves out there.
Yeah. Yeah.
Now, the
Definitely.
upcoming events here on the slide, you can see the April events that are still coming up. We have a Highway 4-star party, high altitude coming up, and then again, the April 29th potluck we mentioned. And then you can see the May events. Naturally, they're on the calendar and then the newsletter. Please note that May 17th, Jeff mentioned this, that the lunar occultation of Jupiter around dawn. So that should be kind of a cool sight to go out and try and observe.
Indeed,
I don't know what the moon's like at that time, but
I won't be here.
okay. And then to the public outreach events, starting off the 22nd at the Lodi High School. April 23rd is Earth Day. That's our big day out at Victory Park. Hopefully you all can come out for that, even if it's just as a visitor or to meet the public there at our booth. We're going to have our solar scopes out there, and it's always a lot of fun and a lot of good activities going on in the park that day. April 28th, Sky Tours at Delta College. That has really been a kind of a cool evening to have the students come out, and they're bringing their telescopes out from the Delta College astronomy class that is going on there. And so we're really enjoying it, even though they're right in the middle of the Stockton light pollution, but it's still kind of nice to see everybody coming out. We talked about April 29th and then the dates coming up in May. So with that, then I will, I want to thank everyone for coming tonight. Stick around for just a moment. Eric and I have a special presentation for you. I think you're really going to want to see this. Meanwhile, I want to thank Darlene and Frank for bringing the snacks and goodies, Doug, and for the coffee. Eric, as usual, let's give Eric a hand. Eric comes early. He sets up all this gear for the AV, conducts the Zoom meeting. He's got his hands full. I'm not even sure he is enjoying the meeting himself at all, but he's doing a great job for us. So thanks,
Now,
Eric.
did you say gear or beer?
Beer, beer.
A little both, yeah.
Okay.
Takes a little
Okay.
bit.
Ooh.
Okay, go to the next one first, Eric, the big one. Yeah. So I don't know if any of you saw this.
Horrendous.
It just came out. The James Webb Telescope just delivered some new images of Uranus, and the images are fantastic. These images were taken on February 6th. It's a single 12-minute exposure. Can you make that larger, Eric? Yeah, I'm going to work with it here. Wait till you see this. These are images of Uranus we've never seen before
Wow.
that show a lot. So let's walk through some of what's going on here. First of all, this was taken with the James Webb NIRCam, the near infrared camera. So it's in the near infrared and two different wavelengths, kind of a blue wavelength and a little bit more. Most of it looks blue, but this is a image of Uranus that, remember that Uranus has an axis that is tilted. So it's like not orbiting the sun. It's more like rolling around the sun because
It's on a 90-degree tilt.
90-degree tilt. It's a good way to put it. So the axis is facing the sun. So that bright spot that you see there in the center, that's actually the North Pole cap, the north cap of the, and so there's actually an ice cap shown there. These other two bright spots you see are clouds. So what we can see here is the weather, the atmosphere, the moons, and naturally the glorious rings. Now, and also in this image, what else can you see?
The
There's galaxies.
Yeah,
Yeah,
lots
is
of
that
galaxies.
Amazing. Galaxy.
Yeah. Yeah, that the resolution is great on Uranus, and then it's actually
Amazing.
great beyond
Yeah.
the solar system. So Uranus, when it's at its closest to Earth, is 1.6 billion miles away. So that just gives you some perspective. The rings, well, we've got another photo of the rings that's a little bit closer up. We'll actually see
Beautiful.
11 of the 13 rings are visible. Now, we first saw the rings of Uranus when Voyager imaged it in 1986.
Yeah.
Real faint images of the rings, but they counted 13 at the time. So I can't quite count 11 here. Maybe you can. And that inner one is kind of a dirty ring, if you will. It's very, very faint in there.
What is that red spot that's sort of off to the 9 o'clock area? Is that like a star behind the planet?
I only see 8.
Yeah, that area there,
That-
kind of oranges.
That red spot, what I understand is that's a cloud. And then those are diffraction spikes that are coming off of that cloud. It's so bright.
Very interesting. That's cool. It's neat on that other image how the diffraction spikes come out of the rings and not from the planet itself. If you went back to that other image, I thought that was kind of interesting. It's just
Wow. It's beautiful.
Yeah.
Yeah, you can see the characteristic James Webb diffraction spikes here, the
Yeah.
5 spikes.
it's just cool how that area inside the rings is still dark but And there's no
Yeah.
diffraction in there, but the planet's the
Yeah.
brightest spot. Interesting.
Right.
Very cool.
Right. And then in this image, we can see 6 of the 27 moons of Uranus. And I didn't know this, but did you guys know that the moons of Uranus are named after characters in Shakespeare plays?
No.
Yeah, Tatiana and Oberon. I think it's from A Midsummer Night's Dream.
Yep, the Midsummer
Uh-huh.
Night's Dream, right?
Yeah.
Puck.
Those are the
My
only two I
favorite
knew, but-
character, Puck.
Yeah.
Yeah.
Pretty terrific images. So James Webb now will have imaged all the outer planets other than Saturn. So I'm waiting for the Saturn image, because if the Uranus image of the rings is this good, that can you imagine what the James Webb image of the of Saturn and its rings is going to be like? It's going to be pretty fantastic. So
You know, when I look at this picture here, considering the glare and the diffraction, I'm amazed at how bright the galaxies show up. Generally, weaker objects, you don't see them because of the glare of the primary objects, but those are really clear.
I was surprised by that too, that the resolution is such that it can both focus
Really?
on and then things beyond our solar system.
Mhm.
No, any other comments or questions or? Okay, well, with that then, I think that concludes our meeting unless there's any other business anybody wants to bring up. We'll look forward to seeing you in person at the April 29th or any of the other events prior to then.
Okay.
Hey, thank you.
And,
This was great.
Yeah, thank you. It's
This is really
fantastic.
great. Thank you, guys.
Yeah.
Thank you all for
Thank you.
attending on Zoom. and here in person.
Eric,
So-
thank you again.
Yeah, thank you.
I'm gonna end recording.
All right.